Hello, welcome to another edition of Calculus 3. Today we are going to do some exercises related to surfaces in 3D. So I'm going to open the book on one of these exercises and we'll see what it is about. So one of the question is, how do you see it? We are looking at a graph of a paraboloid from different vantage points, and the question is, where is it that you are standing for the surface to look the way it is? So it's kind of an exercise you see in engineering graphics quite a bit. Here we are just doing a short exercise and moving on. So in the very first case, we are looking at this paraboloid, equation z equal to x squared plus y squared. We are standing somewhere in space to look at this the way it appears here. The question is, where are we standing? Well, the way these axes are drawn, it means that we must be sitting right on the x-axis itself, because the x-axis doesn't show up anymore. It has been reduced to just a point. So which one of these vantage points corresponds to be somebody standing on the x-axis? Well, of course, this is the only one that matches the requirement, because y and z have to be 0. So how about this picture B? Where do you think I'm standing? So you think about it for a second, and of course you need to look at the picture. So let me go back and you see the picture. So where am I standing for this to look the way it does? You see that all three axes are visible, so I'm not standing on any axis anymore. I'm standing somewhere in between all three of them, and it looks like 10, 10, 20 is perhaps the place I am standing at. That's the only one that it matches the requirement. All the other ones you are standing on one axis. So in part picture C, where am I standing? So here's the x-axis and y-axis. I see them. I don't see the z-axis. It means I'm standing on the z-axis and looking down on this thing, or looking up at this thing. So in this case, if you are on the z-axis, then this is the only possible choice you could have, and so on. So you go ahead and do several exercises like these. Then we have a set of exercises related to surface of revolution. So let me explain one of these exercises, and here is a shorthand for covering all the cases. Let me do one problem, and then we see what does this table refer to. It's just a quick way of answering these type of questions. So one of the exercises here in the textbook says consider the graph of, so consider z is equal to logarithm of y as a graph in as a graph in yz plane. And suppose this is taken and rotated around the z-axis. So we take this thing and rotate around z-axis. The question is, describe the resulting surface and give the formula. What's the equation of resulting surface? So we want to find this equation. So let's quickly get a feel for what this thing looks like. So suppose this is my z-axis, this is my y-axis, and say this is my x-axis. So in the excuse me, I have recorded this thing incorrectly. Let me just correct. So this is logarithm of x, and this is the xz plane. Doesn't make a difference, it's all the same, but I just to get a sense for this thing, we are going to focus on the yz plane first. So yz plane, let's color it like this so that we know what plane we are looking at. So this is the yz plane. Excuse me, making the same mistake. XZ plane. In that plane, z is equal to the logarithm of x. So when x becomes a small number, z is going to become negative, so z is going to go down, and as x increases, z is going to increase gradually. So we are going to have a picture looking like this perhaps. Let me see if I can. So this would be 1, and the logarithm of 1 is 0. And so if you want to color the rest of it also, so this is down here is our xz plane. Here, this is the xz plane. That yellow thing is the xz plane. And we have some graph for what this equation looks like in that plane. We don't really need the details of the graph, but it's good to have an idea. We are taking this thing and rotating it around the z-axis. So whatever this thing is, how far it is going to rotate around the z-axis. So what kind of a surface do you think it's going to make when we rotate it like that? Well, when you take this red thing and rotate it around, it looks like it's going to be kind of a funnel with infinite tail going all the way down here and getting infinitely thin down there. So the question is, what is the equation of this? So when you're going around, you want to think about this thing as the radius. So as we go around, the radius around the z-axis is given like that. So here r is given as the logarithm of x. Well, as I go around, I have to think about this thing as a logarithm of r. Z is equal to logarithm of r, and r itself is going to become x squared plus y squared square root. So if you want to think about it like this, z, you can think about it as a logarithm of r, where r, as you go around here, r is square root of x squared plus y squared. So if you wish, you can just say that z equation of that surface is going to be the logarithm of square root of x squared plus y squared. So the question is, what if I want to do this thing quickly, that I want to go from here to this answer? It's always best to draw a picture and convince yourself as to what is happening, but the table here is trying to make it short. So we have an equation that is in xz plane. Here's the xz plane. I have two of them actually. I can take my picture and rotate it around either the x-axis or the z-axis. Either of these two possibilities are there. And then the question is, one of these variables is going to be replaced by square root of that variable and another one. So if I'm rotating around the z-axis, then x gets to be replaced by square root of x squared plus y squared. Notice the pattern. These two are just these two variables, and the variable for the axis of rotation does not show up inside our radical. So what is it that I'm supposed to do here? I have an equation that is written with x and z. So this is original equation has x and z's in it. The axis of rotation is z-axis. So what we are to do is to replace this x by square root of x squared plus y squared, and that is what our final formula here is. Of course, you can take this thing and modify it in all sorts of ways. For example, this square root can come out of this thing, it becomes a 1/2, or you can exponentiate both sides, becomes the exponential of z is equal to square root of this, and all sorts of different ways you could write this thing in. Another type of exercise you come across in this section is doing the reverse of this thing, meaning a surface is given and you have to find the curve. So a surface of revolution is given and you have to find the curve that was the generating curve of this surface. So here's an example. Suppose we are given a surface 2x squared plus say 2z squared minus say 3 cosine square of y is equal to 0. What we are trying to do here is to find generating curve of this surface of revolution. So if you want to know what this thing looks like, you can go to that website we had and just type it in and you see an interesting picture. Here remember, in the surface of revolution there are always two variables whose squares are added up. Okay, and there are always two variables. Of the three, two of them are squared and added up. The third one becomes the axis of rotation, the one that is not in this mix, and you have a choice of two ways of creating that curve. So let's go ahead and do that example here. So to see it clearly, let me factor 2 out of this thing. You see that x squared plus z squared show up, minus 3 something else. When these two show up, the third variable is going to be the axis of revolution. So we can always say right away that the presence of these two means axis of rotation is y-axis. So the element, the variable that's not here, that's the axis of rotation. And if you want to get the generating curve, you just slice this surface either with the plane x equal to 0. So if you can say x equal to 0, if x is 0, this just boils down to 2z squared minus 3 cosine square of y equal to 0. So that is a plane, that's a curve that is in the z. So this thing is in YZ plane. Whatever curve it is being rotated around the y-axis, and that results in this surface. Or you can take this and slice it with z equal to 0. If you slice it with z equal to 0, you get just 2x squared minus 3 cosine square of y is equal to 0. Of course, in which plane is this thing sitting? Well, look at the variables we got. That's where it is sitting. It's sitting in xy plane. So it is your choice to report this or report this one. Either way, you have the so the generating curve that we are talking about. The generating curve, you can state that is the generating curve, or you can state this is the generating curve. They're sitting in different planes. The axis of rotation is, in this case, just y-axis. Okay, there are many interesting problems in this section. The more of these things you do, especially from the textbook itself, as opposed to the software. If you go there, you see lots of exercises. Not all of them are in WebAssign. So here, let's take a example. We have talked about hyperboloids and such. they come with their own kind of asymptotes, and the problem 49 here is looking at a hyperbolic paraboloid. So we have a hyperbolic paraboloid z is equal, so this is problem 49, z is equal to y squared over b squared minus x squared over a squared, and the problem is asking you to find intersection with a plane is given here. A plane is given with bx plus ay minus z equal to 0. So here we have a hyperbolic paraboloid. It's paraboloid because it's just a z. It's hyperbolic because these two have different signs. And this is, of course, is just with a plane. This is just a plane because it's a linear equation. How do they intersect with each other? So we are going to practice intersection of surfaces in 3D. Well, in this case, the problem is not too complicated because we have z is equal to, so I can write the equation of the plane as z is equal to bx plus ay. And if this wants to intersect that, then well, their z's are going to be the same. Therefore, if I set these two equal to each other, and then I'll have some lead to what the intersection is going to look like. So I say y squared over b squared minus x squared over a squared has to be equal to bx plus ay for an intersection to happen. Okay, now next question is what is this? What kind of an equation is this? Let's bring everything to one side. So I'll have y squared over b squared. Let me put my other y next to this, and then minus x squared over a squared, and then put another x next to this thing equal to 0. Well, what is that one? So that's an equation of something that you have seen in either pre-calculus or calculus and such. We have y squared and x squared, so it's a quadratic curve, whatever it is, and these two have differing signs. So on the first attempt we might think that it's a hyperbola or something, but let's go ahead. You remember a basic procedure we had, a completion of squares, that helps us to find center of our picture. So what I need to do here is to complete the square to see what to do next. So the question is, if I have these two terms, y squared over b squared minus ay, what should I add here? So it's a question, what should I add here so that these three terms becomes a complete square? So I want to make a complete square here. These three, to make it a little bit easier to look at, let me factor a minus out of it. So I'll have x squared over a squared. We are factoring that minus, so it becomes bx. Same question here. What should I add here for these three to become a complete square? And of course, on the other side, we have to, so let's make perhaps put double question mark. To keep the balance, I have to add and so I'm adding this, whatever number is here, so I add it on the other side. This number is being subtracted here, so I have to subtract it from the other side and see what to do next. So here's a question. So let me delegate it to you, that you are going to think about it, maybe 1 minute, 2 minutes or something it takes. How do you complete the square here? So a question from high school, really. What quantity do I need here to make this thing a complete square? So whatever this is, so of course some quantity squared, let me write it like m squared. Then square root of this, square root of that have to be subtracted and squared, so I will have at y over b minus m squared, so that from this expression I get that. From m squared I get this expression, and our clue as to what the m is going to be is that twice the product of these two has to be that term. So twice the product of these two is going to be minus 2y over b times m, and here I have minus ay. So of course I cancel the y's, cancel the minuses, and from this I get that m has to be equal to what then? Let me write this thing better a little bit. So this is the term I have here is ay. So m has to be a times b over 2. So the quantity I am adding here is going to be a squared b squared over 4. Same thing here. You do that here, you'll see that you have to add a squared b squared over 4 here. So you're adding and subtracting the same thing. So on the other side we are going to have just 0. So let's go ahead and do this thing. So let me erase these items here. So I'll have y over b minus, so here we said it has to be a b over 2 squared. Let's double check. When I square this thing, well, of course I get that. Twice the first and second. Twice cancels this 2. This b cancels that b, and I'll have my a there. So that's right. Minus, same thing here. So it's going to be x over a. And this one, because of a plus sign, is going to be ab over 2. So I need to add a squared b squared over 4 here. I need to subtract it here. So when I add and subtract them on the other side, I get I get just 0. When next question comes up, what is the equation of that? Let me remind you of a very basic exercise from algebra. So if you have a squared minus b squared equal to 0, do you remember what happens there? You factor it, so it either tells you a minus b 0 or a plus b 0. So if I have difference of these two, I can factor it like this. It becomes y over b minus ab over 2, then subtract the other one from it, minus x over a plus ab over 2. So this is one factor, and the other factor is the sum of these two. So it's going to be y over b minus ab over 2. That's the first expression. And then the second expression, x over a plus ab over 2. So rather peculiar thing is that the right hand side is 0. If the right hand side was just a non-zero number, this would have been an equation of a hyperbola. But when it is 0, when you simplify this thing, you see that all you get are just two lines. Let's go simplify here. So this becomes y over b minus x over a, and this and that together becomes minus ab. Here becomes y over b plus x over a, and these two cancel each other out, and I get this. So either this factor is 0 or that factor is 0. So let's record it. Our conclusion is that if these two surfaces, so let's remember what happened that we ended up here. We had a hyperbolic paraboloid. Some peculiar plane was given to us, and the question is, what's the intersection of these two? So we set the z's equal to each other, we simplified, and we came across an equation, a peculiar equation. In general, this would have been, if we had moved our plane around somewhat, this would have been a hyperbola, which tells us how you cut this thing, you get an equation of hyperbola. But in this case, when it is 0 on the right hand side, it boils down to two lines. One line is y over b minus x over a minus ab is equal to 0, and the other one says that the y over b plus x over a is equal to 0. We can leave this equation as it is. To simplify perhaps a little bit more, we can try to find the z also. So here, if I find my y becomes minus bx over a. Here, if I find the y becomes plus bx over a plus b times ab, that becomes ab squared. Now I can take these equations and plug them into either of these two. Let's say the second one is easier, bx plus ay. So in either case, z was equal to bx plus ay. So if I take bx and ay and add it here, I get z is equal to 0. So that's a simple line. Whatever line this is in the xy coordinate plane, with z equal to 0, that line just sitting on the xy coordinate plane is not going off the plane. In this case, if I take bx plus ay, if I multiply this thing by ay, I will get bx plus a squared b squared, and so my z in this case becomes 2bx plus a squared b squared. So the intersection of these two planes, we have the intersection is either you're sitting on the xy plane with z is equal to 0, and in that plane y is equal to minus bx over a. This is one intersection, and the other one is y is equal to bx over a plus ab squared, and the z is 2bx plus a squared b squared. So the intersection is a pair of line from their slopes. We can tell they are going to be perpendicular to each other. So the intersection of these two are just these pair of lines. Now again I want to encourage you to try your answers with that software we have been using throughout the semester, CalPart 3D. Here is I have entered an example. I took a and b to be 1 so that the picture is visible. So our hyperbolic paraboloid is just y squared minus x squared, and our plane in that case with a and b being 1, it just boils down to just x plus y. When you look at the intersection of these two, you see what the intersection looks like. We have one line going in this direction and another line going in the other direction. These are two intersection points. To make the picture perhaps more visible, let me remove the plane itself. So here is our hyperbolic paraboloid. We said this kind of things look like a saddle. So this thing is a saddle. Now the other one, let me take this thing off and just put the other one. The other one is just the plane. Okay, just an ordinary plane. When you intersect them, well, you are looking at where do they hit each other, and okay, at home probably you will have a better view. We said to increase the number of grid lines to see less pixelation, and these jagged edges here is going to become smooth and everything's going to look straight and nice. Okay, many other examples in this section. We are going to move on to the next topic, which is cylindrical and spherical coordinate system in the next lecture. And until then, good luck and God bless.